Hey guys, this is CHEMPLIFIED and today we will talk about non-ideal solutions. This is the second video for non-ideal solutions. If you want to watch the first one, you can watch. It is just below this video on the channel. Now, let's start. In the previous video, we talked about non-ideal solutions having positive deviation from Raoult's law, and in this video we will talk about non-ideal solutions having negative deviation from Raoult's law, right? So we will come directly at our topic. We will not discuss about the interactions of non-ideal solution. We have done it in the previous video. Now, for non-ideal solutions having negative deviation from Raoult's law, in these solutions, AB interaction are stronger than AA and BB interactions. First of all, I repeat once again, whenever I am talking about the term interactions, I am talking about force of attraction between the particles. Here I am talking about force of attraction between AB, and here I am talking about force of attraction between AA and BB. Now, after calculations, we find that partial pressure of A is less than P naught A XA, and partial pressure of B is less than P naught B XB. And also total pressure is less than the pressure calculated by Raoult's law in case of ideal solutions. Right? Now, the main question is why the total pressure is less than the calculated vapor pressure. Why the total vapor pressure or the observed vapor pressure is less than the calculated one. Why it is happening? Because total vapor pressure, why this is happening? Because of the term interaction. Sorry, I was started reading the statement. Because of the interaction between the particles. Now, increase in pressure or decrease in pressure, how it depends on interaction, we will talk about that. But first, let me draw a diagram. Consider the diagram 1. It is already written in our statement that AB interaction are stronger than AA and BB interaction. In the first diagram, there is only component A present, and since the interaction between the particles A and A is not strong or not nice, the particles try to remain far from each other. That means the solution is volatile, and it will show its volatile behavior by increasing the vapor pressure on its surface or on the surface of the liquid, right? Now consider case 2, the second diagram. In this, what we have done is we have mixed the two components A and B together. Now since we know that AB interaction is stronger, so particles of A and B will try to remain close to each other. They have a good bonding with each other. They do not want to evaporate, and since they don't want to evaporate, because they already have a strong bonding with each other, the total pressure will decrease. The total pressure above the surface of the liquid will decrease because of the bonding between the two components, right? That's why the total pressure is less than the pressure calculated by Raoult's law. Now, in the next statement, it is already written total vapor pressure is greater than the sum of, sorry, less than, total vapor pressure is less than the sum of, it is written greater, it is less than the sum of individual vapor pressure. Now comes the most important points, delta H and delta V. Delta H, delta V. Change in enthalpy is less than 0. Change in volume is also less than 0. Why is this happening? Change in enthalpy of mixing is less than 0 means the process of mixing of the components A and B, or the process of dissolution, is a process in which heat is released or heat is evolved. Now, why heat is evolved? Remember, our component A particles are not showing strong interactions. The force of attraction between them is low. So, the breaking of bond between AA and BB is easy. And since the interaction between AB is stronger, the formation of bond is also easy. And since the formation of new bond is easy, some amount of heat is evolved. some amount of heat is released, and the components get stabilized. That's why delta H is less than 0 and exothermic in nature. Now why delta V is less than 0? Why delta V is less than 0? Look at this diagram. Now A and A have less interaction or less force of attraction between them, right? Since the force of attraction is less, they will occupy greater volume. And in second case, since particle of A and B have strong interactions, they will come close together because they have strong bonding with each other. They will come close together and the volume will decrease. The volume of the solution will decrease. That's why delta V mixing is less than 0, that is volume is decreased during the dissolution or the mixing of component A and B. I hope I made you understood these 2 points very clearly. Also why total pressure is less than the calculated pressure. Now always remember, for non-ideal solutions showing negative deviation from Raoult's law, the escaping tendency of both the components A and B is lowered, which shows lower vapor pressure than expected ideally. Now I already talked about it, but let's repeat. The escaping tendency increases if the solution is volatile or if the component particles do not show any kind of force of attraction. But we know that in solution A and B have greater force of attraction, greater bonding. They want to stay together, which means they don't want to evaporate. If they don't want to evaporate, you have to increase the temperature, but the temperature should always remain constant. At a particular temperature you see the vapor pressure, so at a constant temperature the vapor pressure will decrease. Now in case of pure component AA and BB, in case of pure component AA and BB, the interaction is not good, means the liquid is volatile in nature, and due to which its escaping tendency is more. But in this case, since force of attraction is high, the escaping tendency of the component A and B is less. Just remember that. Now let's move. This is the graph. The white line shows the graph of ideal solution, and the yellow dotted line shows the graph of non-ideal solution, that shows negative deviation from Raoult's law. If positive deviation is there, you will make a graph like this. Now since negative deviation is there, I have drawn it below the line, right? This is the total pressure, this is partial pressure of component B, this is partial pressure of component A, and these are the three lines which shows total pressure, partial pressure of A and partial pressure of B. Remember this graph? This is the graph for non-ideal solution that shows negative deviation from Raoult's law, right? Now these are the examples. You can pause the video and check them out. These are the example that shows negative deviation from Raoult's law. I hope you understood today's video. This is it for today's video. Thank you very much for watching.